Medical imaging is used to understand what is going on inside the human body and prescribe treatment. With new image processing and machine learning techniques, the traditional machine imaging techniques such as CT scans can be enriched to get a more sophisticated diagnosis. HeartFlow uses data from a standard CT scan to model a human heart and understand blockages of blood flow using simulations of fluid dynamics. In today's episode, Razik Yousfi and Grady from HeartFlow describe the data processing pipeline for the company and what their technology stack looks like. We discuss AWS, we discuss biology, we discuss a lot of different topics, and this was a really enjoyable episode at the intersection of biology and computer science. Every software project uses email. Every time an e-commerce site processes a transaction or a user makes a comment on a social network, email notifications are sent. SparkPost provides email delivery services for apps and websites. To try SparkPost and send 100,000 emails a month for free, go to pages.sparkpost.com/sedaily. SparkPost has a range of pricing options, from free self-service packages to sophisticated enterprise support and services. Start sending emails to your users today. Go to pages.sparkpost.com/sedaily to send 100,000 emails a month for free. Thanks to SparkPost for being a new sponsor of Software Engineering Daily. And if you want to send 100,000 emails a month for free, go to pages.sparkpost.com/sedaily. Grady and Razik Yousfi are engineers at HeartFlow. Razik and Leo, welcome to Software Engineering Daily.
Hi, Jeff. Thank you for having us.
I've been trying to do more shows on the intersection between biology and engineering, so I think this is a great fit. HeartFlow uses data from standard CT scans to model the human heart and understand blockages of blood flow. And we're going to walk through how that works, including some machine learning techniques. But I want to start at a high level so that people understand what this domain is once we start diving into the engineering aspects of it. So let's start with the idea of cardiovascular disease. What does that mean?
Coronary artery disease is the number one cause of death in the world. So 1 out of 3 people die of coronary artery disease. And the coronaries are the blood vessels that feed the person's heart. When one of those gets blocked, you can have a heart attack and die or have a severe impairment.
How preventable is coronary artery disease once it's identified?
Well, it depends on the severity, and there are multiple different treatments available. So at the lowest level of severity, the disease can be treated with medication. And going up from that, it's a stent. So a stent's a little metal tube that you put inside the artery and you open it up to open up the blockage. And then if the patient has very severe cardiovascular disease, then the next step would be bypass surgery. What we focus on here at HeartFlow is the decision between medication and a stent, which can be a very difficult diagnosis to make for the physician.
Describe what classic CT imaging is.
So CT is computed tomography. It's an X-ray in 3D. And what it does is it enables you to look at a 3D, very high resolution scan of the patient's anatomy. And it was performed with sufficient resolution, both temporal and spatial, about 10 years ago. And that's when cardiac CT got on the market in the first place to assess coronary arteries. And with CT, typically you can see whether there's a blockage. The problem with CT by itself is you can't really determine how severe it is and how obstructive it is to blood flow.
So a doctor does a CT scan, looks at the CT scan, and then makes a judgment of what the treatment is going to be. And because of the limited fidelity of the CT scan, sometimes that treatment may be not the best course of action.
Yeah, that's right. So with CT, basically you can tell whether the patient has disease or not. But if they do have disease, you can't tell how much blood is really being prevented from getting to the person's heart. So usually the next step after a CT is you say, okay, well, this patient has disease, and they go for an invasive test. And in this invasive test, what will happen is they will actually take a catheter, they'll go inside the patient, push it all the way through the vascular system, and they'll measure the blood pressure before the blockage and after the blockage. And then they see, based on the change in pressure across the blockage, how severe the cardiovascular disease is for that patient.
That sounds like an unpleasant procedure.
It's unpleasant. It's dangerous. There's something like a 1% mortality rate for
just for the test.
Just for the test, yeah. And it's also expensive. And the big issue, too, is that about 75% of the time when you do this test, you find out that the patient has non-obstructive disease to the point where you can treat the patient with medication and you don't need a stent. So what we're trying to do is prevent that test from being done unnecessarily by doing this test effectively, completely non-invasively, just from the CT scan.
So we're going to get into how that works. The idea is that by taking the CT scan imaging and putting it through some machine learning, some image processing, you can avoid this challenge of taking the blood pressure before and after the blockage so that you can model how this blood flow is going rather than taking these direct measurements. So you're going to be deriving from fluid dynamics based on the imaging how the blood is flowing. So at a high level, how accurate is that technique relative to the technique of taking blood pressure measurements before and after the blockage?
So what we do is we extract the anatomy from the patient's CT through a series of computer vision algorithms and machine learning techniques. And then based on that 3D anatomy that we extract for each patient that comes to us, we then use, as you mentioned, computational fluid dynamics to calculate the blood pressure before and after the blockage. We've done now 3 big clinical trials to validate the accuracy, and we are we're in the last one was somewhere in the low to mid 80% in terms of accuracy. What that means is that there is a cutoff clinically of 0.8, which is the ratio of the blood pressure before and after the blockage. So above 0.8, you say the patient doesn't need a stent. Below 0.8, patient does need a stent. And so when I'm talking about accuracy, it's being our calculation is on the same side of that 0.8 cutoff as the invasive measurement.
Now that we have an overall picture of the idea of what HeartFlow does, Razik, maybe you could talk a bit about the software architecture of this process. You gave a talk at the O'Reilly Software Architecture Conference a while ago, so I know that you're talking about this, you're thinking about this a lot. Give me an overall idea of how HeartFlow's software works.
We initially start by ingesting the CD image out of the hospital's infrastructure. And to do so, we deploy a thin virtual appliance within that hospital's infrastructure that connects directly to the CT scan at the hospital. The role of that thin virtual appliance is to basically send us the data to our cloud infrastructure. Once we have received the data, we process that entire data set with a bunch of machine learning and deep learning algorithms. And that is a computationally expensive process. But by the end of it, we have a high fidelity 3D model of the heart and coronaries. Once that 3D model is generated, we review it on premises by trained HeartFlow technicians that are pretty much correcting the model to generate a very accurate and precise model definition. After the model has been generated, we then send it to our computational fluid dynamics algorithms, and we solve it to pretty much compute the flow at all the different points in that 3D mesh. Once the mesh has been solved, we then use a couple of techniques for off-screen rendering, and we automatically generate a PDF report that contains images with the different FFRCT values pinned onto that model. We have that report being reviewed, and once it's reviewed, we ship it back to the customer. Breaking
this up into the different components of that pipeline, The first step is you've got that classic CT scan that we've had for a decade, this technology, and you put that CT scan into a HeartFlow analysis, and you get a patient-specific anatomic model of the arteries. What are the algorithms and the software that are involved in converting that CT scan into that anatomic model of the arteries?
Yeah, so I'm going to start at a very high level, and then Leo can maybe dig into some of the details of these algorithms. But what we typically do is we pretty much have a lot of algorithms written in C++, and we have a pipeline that's written in Python, and we run a bunch of different stages to extract the aorta, the center lines of that 3D model, the lumen associated to these center lines in that 3D model, and we pretty much generate a final mesh out of that. Leo, maybe you want to dig into more specifics there?
Yeah, so in order to perform the calculation for the fluid dynamics, we need to know, as Razik mentioned, the lumen, which is the area of the artery where blood can flow. We also need to know the overall mass of the person's heart in order to be able to calculate the demand for blood in that patient. So all these things get extracted using a series of computer vision algorithms, shape models, and medical imaging analysis algorithms that have been trained using our annotated database using deep learning.
Are these algorithms that have been around for a while, are they off the shelf in some sense, or was it mostly having to write everything from scratch yourself?
One of the interesting things that we have to face, so I've been in medical imaging now for a while. I worked at Siemens for a long time, which dealt with a lot of these medical imaging analysis problems. And one of the challenges that we have to deal with is both robustness, trying to deal with multiple different scanner vendors, multiple different geographies, artifacts, noise, and so on. But the other is the level of precision that's required. So if we are off by just a voxel or two in terms of estimating the size of the person's coronaries, that can have very profound impact in the patient's CFD calculation. So in other words, we need an extremely precise and extremely accurate image segmentation, which is what provides us these 3D models. And that's different than what's been existing in the field. So we haven't been able to use just off-the-shelf components. We've had to really build a lot of our own. As you're probably familiar, Jeff, deep learning has really come on the scene very strongly in the last 4 years or so. So a lot of that work is all fresh and new, and there are multiple different companies that have been taking different approaches on it. We've really been tailoring these algorithms and these architectures to our specific system and our specific problems.
When I'm choosing the tools for my side projects, the first thing that I look for is ease of use. That's why I love MongoDB. It is the most popular non-relational database, and it is super easy to use. At the beginning of a project, I often don't know the shape of my objects, and Mongo makes it easy to evolve the database schema as I like over time. Over time, as my project gets popular, I'm going to need to scale, and thankfully, MongoDB has built-in horizontal scalability, but configuration and database maintenance aren't really what I want to spend my time on. Thankfully, MongoDB Atlas was released in 2016. MongoDB Atlas is the easiest way to get access to MongoDB without having to run the database yourself. You pay only for what you use, from small projects all the way up to large production deployments. To try MongoDB Atlas today, go to mongodb.com/sedaily and get a free $25 in credit. Use promo code GOATLAS25 to get that $25 in free credit. Atlas is the only hosted MongoDB service built by the engineers behind the database, the company MongoDB. With Atlas, you get end-to-end encryption, you get VPC peering, you get access to the latest releases, and for a limited time, you can go to mongodb.com/sedaily Enter promo code GOATLAS25 and get that $25 in credit and get started with MongoDB Atlas. Thanks to MongoDB for being a new sponsor of Software Engineering Daily, and thanks for being the database behind a lot of my favorite side projects in the past. We're really happy to have MongoDB as a new sponsor of Software Engineering Daily. My limited understanding of what makes a problem a good character, a good fit for deep learning is you've got a giant sample of data and you're not sure how to label that data. You're not sure how to extract features from that data. But you've got such a large data set that you can tell the deep learning algorithms, hey, give me some features that are widely represented in this data set, or find some themes, or could you give me an idea of, let's just talk broadly about what makes a problem a good application for deep learning? Because I know deep learning doesn't solve everything.
No, it doesn't. But one of the areas of real strong success for deep learning has been in imaging and computer vision problems. So We're lucky in that sense. And you're right that the amount of data and the amount of annotation in the data really makes a difference in terms of your ability to be successful with deep learning. I think one of the reasons that machine learning in general has not been very well applied to medical imaging has been not a lack of data, but a lack of annotations for those data sets. So if you take a typical hospital, they can have thousands, tens of thousands of patient scans, but they're just a collection of pixels. So they're just completely unstructured data. The value comes in having both the pixelated data and somebody to go in and say, okay, well, this region is the heart, this region is the vessel, this is disease, and so on. And that is much harder to come by because doctors don't do that on a day-to-day basis. But HeartFlow, because of our business model as a service company, a cloud-based company, we are able to achieve not only a large data set, but also a large amount of annotations, because every patient that comes through, as Razik mentioned, not only do we run our automated pipeline, but we have trained technicians who make corrections and edits, and then we can feed those back into the learning system.
Now, you do need annotations, you're saying? You do need the images to be annotated and labeled?
Classically, deep learning is applied in what's called supervised learning situations, where you have both the data and the training of what you're looking for. There are also efforts in unsupervised learning, but supervised learning is much more of a solved problem, or much more of a better controlled, better conditioned problem. So fortunately, we're in that position where we have both the data and the annotations, and we can really leverage deep learning to its hilt.
So what defines a deep learning solution versus a machine learning solution? Like I've understood a little bit about machine learning for a long time, in the sense that you've got, if you've got labeled training data, you can put that labeled training data into an algorithm, and it will identify the themes that are associated with those labeled features. So what is different about deep learning?
Yeah, that's right, Jeff. So deep learning is a subset of machine learning. It's a set of techniques that are based around artificial neural networks. And artificial neural networks have been developed for decades, and they've kind of come in phases. In the 80s, then they went out of favor, and then came back in the 90s, and then went out of favor, and they're back now. And basically, with every iteration of these artificial neural networks, there have been a substantial number of improvements to them. And one of the things about deep learning that makes it deep is that there are artificial neural networks with multiple different layers, often many more layers than have been used in the past. And previous iterations of neural networks with lots of layers ran into trouble in terms of training them and basically not being able to harness large amounts of data sets in order to achieve full training. But based on multiple improvements over the last decade, a lot of these problems have been solved. And so now using machine or neural networks with multiple layers, many deep layers, can be used to achieve really great results. But you achieve better results when you have very large data sets.
Give me an idea of how deep learning is applied to the construction of the anatomic model of the arteries. What are you doing with this giant data set? How are you applying deep learning to it?
The key for us is getting the dimensions of the person's arteries and really understanding the size of a blockage. Unfortunately, it's not that simple. So all of these patients, when they go for a CT scan, they get contrast, and that lights up their arteries so that they're brighter than the background. But there's certain kinds of disease with calcium where you have calcium's much brighter, and so it will obstruct your ability to see the person's vessels. Also, you have complex disease and bifurcations. You have mixtures of disease. You have poor image quality. If you have a large patient, for example, you'll have a lot of noise. And so because the vessels are very small, trying to extract the lumen dimensions, really at the limit of the resolution of the CT, is very challenging. So effectively what we're predicting with the deep learning is the dimension size of the artery at every centerline point along the trace of the vessel.
How do you benchmark the accuracy of the models that you're building?
Yeah, it's a great question. So we benchmark it really in two ways. So one way is by doing the whole system, calculating these blood pressure values and then validating them against the invasive measurements. But another way is to validate just the anatomy itself, the deep learning results. And for that, we have to have a gold standard. The gold standard currently in coronary artery imaging is invasive imaging as well. So you can use an invasive ultrasound probe or an invasive OCT probe, which is an optical probe. And then you can see very fine resolution anatomy inside the patient's vessel. So in some patients...
How close are you getting to being able to mimic that?
So it's interesting. Our correlation coefficient between the CT and the invasive imaging is at a level that is at or exceeding everything that's been published for expert reads of the CT and the invasive imaging. And that's fully automatic.
Wow. Yeah, so there's no invasiveness. So what would be this? Can you give me like more like absolute measurements of like the fidelity, of the HeartFlow technique versus the actual invasive technique? I mean, I totally believe that it's better than anything published, but how does it actually compare to the invasive techniques?
In terms of the pressure measurement, or in terms of the anatomy?
I guess I'm curious about both, but I was more referring to the anatomy.
So we're going to publish on this very shortly with a study that we've been doing with Japanese collaborators, where we have CT and invasive imaging. I'd have to check, but I think the average absolute error we had was 0.24 millimeters, which is less than the size of a voxel of CT.
Okay. I don't know what that means. It sounds reasonable.
It's really good.
So, okay, I believe you. Yeah, definitely. So the next phase, I mean, you say we've talked through this. We've gone really deep on this phase of building the anatomic model of the arteries. And then the next phase is you build a physiology model. What does that mean?
So, in order to calculate the fluid dynamics results, you need to know how much pressure is being input into the coronaries and what the resistance of the coronaries on the very small side are. And both of those you can't measure very easily from a CT image. So we have to use other information in order to estimate these values for each patient.
Okay. So can you talk more about the software that's involved in the physiology model development?
Yeah, this was really the project of our founder, Charlie Taylor, who worked on blood flow modeling and patient physiology modeling at Stanford for almost 20 years before founding this company. But basically, you can use some population statistics and some personalization to estimate the patient's blood viscosity, the input pressure, and then based on the coronary anatomy size at the limits of the resolution of the CT, you can estimate the amount of territory in the patient's heart that's being fed by that vessel. And from that, you can work back to the amount of resistance that is being experienced to blood flow and blood pressure downstream. And then we roll all of this into the calculation for the blood flow and validate that against the invasive measurements.
Do we understand fluid dynamics well enough to model the flow of blood through the heart accurately once we have this anatomic model and this physiology model?
Yeah, it's a great question. So fluid dynamics are really described by the Navier-Stokes equations, and those have been known for, I think, since the 1800s. However, solving them can be challenging and computationally expensive, especially in complex flow situations where you have turbulence and things like this. However, given a domain, given an anatomy, and given the right boundary conditions as determined by the physiology, then it's just an issue of solving these equations accurately and quickly. And this is one of the challenges that we've struggled with at the company, is because the doctors want the results back quickly, but classical CFD can take hours and hours and hours to compute. And so we've had to really leverage the AWS architecture in order to make these computations fast and feasible in a clinical setting.
Now, this gets really interesting. Maybe Razik can talk about this in more detail. I was going to ask about the latency because it seemed to me like, this is not a latency-sensitive problem. You just send the CT scan to the cloud, and you can give it a bunch of time to get a really high fidelity imaging. But it sounds like actually latency is a big deal, and you want to get the results back quickly, and this image processing can take a while. What are you doing on the AWS architecture? Have you built a way of distributing this computation, or doing some kind of MapReduce type of thing? Maybe you want to talk more about how you are leveraging the AWS architecture.
Yeah, sure. So we're actually not doing anything related to MapReduce whatsoever. When you think about, so again, there are multiple aspects. When you think about the computational fluid dynamics, the problem is basically that you need to have a lot of CPU, right? The more CPU you have, the faster the solution is going to converge, and the faster you will get your results. One of the typical challenges is that you are CPU bound on a lot of the Amazon instances, and the easiest way to get around that is by building cluster of machines that you connect to one another and that you make aware of one another, and you use messaging pipelines like MPI in order to pretty much distribute the computing across all these different nodes. Building that setup is to some extent not necessarily challenging, but you need to take into account a couple of factors like the scalability. So the more data you want to process, the more cluster of machines you're going to want to set up all together. And you have to pretty much create this cluster of machines together, but also take them down together. Otherwise, you're going to spend a lot of money. So this is pretty much what we're doing. We pretty much came up with the ideal number of CPU that we need. And we are building this cluster of machines to take the advantage of most of the hardware Amazon can provide us in order to do that. When it comes to the anatomy part, the setup is completely different. It's different because we have a lot of different hardware requirements. Some of the algorithms require a lot of CPU. Some of the algorithms require a lot of memory. Some of the algorithms actually require neither. They can just be run on a very small instance. So what we do there is we're trying to be a little bit smarter when it comes to pretty much running the algorithms on the set of machines that will give us the better performance for what we need to do. Originally, what we did is pretty much just think about it as a minimum instance requirements that we need, and we're gonna find the minimum instance that we need, and run everything there. But what we're currently doing is a little bit smaller, and what we're trying to pretty much schedule based on the hardware requirements, some of the algorithms that will require another GPU, that will require another lot of memory, that will require a lot of CPU, both to save money, but also to be able to pretty much run the algorithm in a much faster time, so that you were mentioning latency, so that we can pretty much finish computing that anatomy as fast as we can by leveraging a lot of the different hardware, yet not necessarily spending a lot of time transferring data left and right.
Do you have an SLA that you guarantee you will finish the rendering in some predictable length of time?
Yeah, we guarantee 48 hours, but we're striving to drive that down to less than an hour as much as possible. And the reason is because every hospital runs at a different tempo and a different cadence. Sometimes they are happy to get the results a few days later, but increasingly as they are starting to rely on our technology clinically, they want the results back quickly. And some hospitals have even started using HeartFlow to address patients in the emergency room, in which case the turnaround time is very, very important for them.
Wow, that's so interesting. It takes 2 days. So
that's what we guarantee. It doesn't take 2 days.
It's right. Certainly,
that's what we guarantee.
But
yeah.
Can you give me some insight on why a computer vision problem like this would potentially take 48 hours when you have things like self-driving car systems that are apparently, I mean, I've never seen a self-driving car in the wild, but apparently they're good enough to be doing this image processing on the fly. They're good enough to identify, oh, this is a tree, this is a person, this is a mailbox, versus where you have a much longer SLA with the heart. What's the difference in the computer vision problem there?
It's not the speed of the computer vision itself. It's the main bottleneck in our system is really around the human component of doing the editing and the checking of what the machine has produced. So because we have such requirements in terms of accuracy and precision, that we have our trained technicians have to go through every case and look at it at a very detailed level. And that can take some time, especially if it's a very complex patient. We see patients with very large amounts of disease, but we also see patients that have anatomical anomalies. We see patients that have very strange conditions. And for those reasons, sometimes it just takes a little bit longer. And the influx of cases is not steady. So there'll be times when we don't have very many cases coming in, and then we'll have spikes with lots and lots of cases coming in. And for that reason, we can just get backed up with this human component, especially if they're complex.
This is, of course, why the demise of the human in the hospital has been greatly overstated. Like in the sense that people talk about, the radiologist is going to be out of a job in 5 years, and it's so clear that the human-computer interaction component of things like HeartFlow, it is only getting increasingly accentuated. Can you talk more about the interaction between, or what the human in the loop does here?
Yeah, they're basically doing quality control on our system and enabling it to handle both outlier cases, but also really ensure the quality of it. And you raise a really great point. I was just at the big radiology conference earlier last week, and there was a lot of talk about radiology in the future and deep learning. And I think one way to think about this is the way that Kasparov has talked about chess-playing computers. So today, a chess-playing computer can outperform any human. However, a human with the chess-playing computer can outperform any chess-playing computer. And Kasparov has talked about this interaction of a human with a computer. He's called it centaurs, that are basically half man, half machine, and can outperform either one by themselves. And I think this is where we're driving toward, both in radiology and here too in HeartFlow.
Yeah, and there's, you could certainly say, okay, well, the centaur situation is just this is only going to last this is something that is not going to last. Like in a couple decades, we're going to get to the point where the Centaur process has successfully trained the computer to do all the work on its own. I think it's very hard to say that with any conclusiveness at this point, especially because like it's kind of conceivable for maybe that to happen with chess, because as complex as chess is, I think chess is a much lower order of magnitude complexity to solve by a computer than something like diagnosing heart disease. I don't know. Would you say that's accurate?
Yeah, we're never setting out to replace a physician in any way. We're really trying to enable the physician to have more information and more data, and take the same CT scan that they've been operating with for the last 10 years and get more information out of it, and really be able to get that information quickly, accurately, precisely, and beyond what they can see with their eye. And armed with all of that additional data, all of that additional quantification, they need to learn how to interpret it. They need to learn how to use that to maximize the benefit of the patient. But that's not something that HeartFlow, that's not something that the computer is going to do for them. It's just going to provide them all of this new information they didn't have before. And it's up to them to figure out how to use it to treat the patient.
Razik, you talked about the idea that you have these very specific hardware requirements for processing the images as expeditiously as you can. Can you talk more about the AWS abstractions that you use? I mean, AWS has all these services that you could use, but they also have just more infrastructure as a service things where you just select what processors you need, and these things are less like AWS specific abstractions. They're more about, do you want an M3 large, or do you want this type of processor or that type of processor? Do you want this type of storage or that type of storage? Are you using the AWS specific abstractions like Kinesis or I don't know, elastic load balancers or something? Are you using these kinds of things, or are you using just more generalized infrastructure technologies?
It's a good question. We actually leverage quite a few Amazon services. On top of the entire image processing or CFD pipeline, we basically also operate websites and databases, APIs, and all these additional components. When you think about those, we are definitely leveraging Amazon to do the load balancing, for example. To do the databases, we're using RDS and we're using MySQL as a database today. We're using a lot of the encryption mechanisms. Encryption for us is extremely important because we need to basically encrypt all the protected health information at rest and in transit. And having a lot of different Amazon services that are built for HIPAA pretty much, and allows us to securely transmit, process, and store the data is something that's really important. And when you look at all these services, we've been able to design a system that relies on buckets, for example, to store all the databases again, like RDS to pretty much store all the metadata, and so on and so forth.
You mentioned compliance. I have heard compliance as something that gets in the way of a lot of people starting businesses in the medical domain. Talk more about what does that term mean, compliance? What kinds of things do you have to do to be compliant or HIPAA compliant?
So there are a lot actually to that aspect. When it comes to designing the system, like I just mentioned, it means handling the protected health information with care. That involves pretty much enabling securely transmitting the data from the hospital infrastructure to the cloud, making sure that the data is always encrypted when we store it, so in the different data storage places. Also making sure that when we process the data and use that protected health information, everything is still secure. So that's one of the aspects of it. The other thing is we have a lot of different regulatory requirements when it comes to storing that protected health information in specific regions. Japan is a good example. We're operating in Japan, but we need to ensure that the protected health information never leaves Japan. So we've been able there to pretty much leverage the Amazon cloud and design a system where we can dissociate the PHI information, leave it in Japan, do our entire case processing in the US and trigger all the different algorithms that we have in the US. And on its way back, we're reattaching that protected health information in Japan and only in Japan. So this is, for example, one of the things that we have to deal with on a daily basis. The other thing is the impact on software practices, where it is very common in a lot of software companies to do continuous deployments, get to production multiple times a day. It is a lot more challenging for us. We have a lot of delays incurred by just the fact that we're regulated. Sometimes you can pretty much come up with a new algorithm that will increase the accuracy, like Leo mentioned, but you cannot just use yet that algorithm in all of the regions because it's not being cleared, or it's only cleared in one region, not the other, and you have to put that on the shelf pretty much and just wait for it to be clear so that you can plug it into your entire pipeline and system and use it. So yeah, these are some of the impacts that compliance have on us on a daily basis.
So you've got a bacon delivery service, and you need to notify your customers when their bacon has arrived at their doorstep. Twilio helps you make sure your customers get the bacon while it's hot. Twilio's programmable API lets you build SMS or voice alerts easily in the programming language of your choice, all in under 5 minutes with only a few lines of code. Now your customers get a text or a call the instant their bacon is ready. If your customers want to see the bacon frying on a hot pan, Twilio has video APIs and SDKs for the platforms that you know and love. Learn more at go.twilio.com/podcast and get an additional $10 when you sign up and upgrade your account. That's go.twilio.com/podcast. You will only pay for what you use, and it costs less than a penny to send a text. Get started at go.twilio.com/podcast. Get your bacon delivery service cooking with Twilio's APIs for voice, SMS, and video. Do either of you have a particular editorial opinion on compliance? Do we have too much compliance? Do we have too little compliance? I mean, I guess we're talking about two different things. We're talking about the compliance that gives people privacy, that ensures their data is private. And then we're also talking about the compliance of building systems that actually work and have been verified by a third party to provide a level of accuracy as a treatment, or I guess as an identification system, identifying coronary or cardiovascular disease. What are your opinions on regulation? Do we have too much of it, too little of it?
Well, I think obviously it's very important for everybody to have their own health data maintained in a private and secure fashion. I don't think any of us really wants that being publicly known or publicly accessible. And I think the regulations are well-intentioned and I think for the most part reasonable. However, it's a patchwork from different countries of how those laws work. And because there's no consistency there, we have to navigate this landscape, which changes and can be tricky. From the software development standpoint, I think that the rules are actually, it's interesting because they are guidelines in a lot of ways for how to do software development. And there are certainly requirements. We are audited by both the FDA and by other bodies in other countries. However, I think because medical device development was traditionally a very slow process, a very hardware-driven process, these regulations are interpreted and classically executed in a way that doesn't fit a software or a cloud-based environment. And so one of the things that we've really been doing is rethinking how to do software development in a very fast, very modern way that still fits within the compliance guidelines. And I think for the most part, that is possible, but it's certainly unusual and it's an area that we're doing things differently from other companies.
What are you doing differently? What kinds of processes have you put in place?
So there are a bunch actually. Just to echo what Leo was saying, a lot of these a lot of these additional mechanisms make a lot of sense. Securing the data of your customers should be done in every software company, right? Ensuring that the product that you put out there is the best product and that you're pretty much checking in every way that you're delivering the best results is something that every company should be doing. That being said, we have a lot of additional delays, and most of the processes we put in place are pretty much ensuring that we control the software at every possible stage in terms of requirements. We have internal cross-functional sign-offs. We're doing code reviews on everything that we're pushing. We're doing extensive testing of all the different bits and pieces to ensure that every piece of our component that gets out is verified by an additional department. And all, in addition to all the best engineering software practices that a lot of companies are doing today.
A lot of times, the way that these compliance guidelines are interpreted are in a classical waterfall setting, and trying to adapt them to a faster iterative development that still ensures all of the quality and all of the compliance and the documentation has been something that's different, and one thing that we've really had to think about how to interpret these guidelines to maintain compliance and maintain all of the quality and the well-intention of them, but to be able to move more incrementally and faster.
I guess you do have the advantage of being a SaaS. Like, even though I'm sure
Exactly.
you have all these difficulties towards regulation, but once you get HeartFlow in place in a hospital and how they're using it, once they go from just doing regular old CT scans to CT scan plus the HeartFlow process, then you've got the SaaS in place, and then you can just push updates to it however you want to. In that sense, you've got the Agile as much as any SaaS company.
Yeah, that's right.
Can you talk more about the process of getting HeartFlow accepted? I mean, I imagine you have to go to these doctors and basically say, I know you've got this practice that you have been doing for years and years and years and years. We want to introduce this other layer of analysis into it. I imagine that can be a difficult process to try to get people to integrate in.
Well, the introduction of every medical technology follows multiple stages. So in the first stage, you're building it, then you have to prove that it works, then you have to get regulatory clearance to sell it, then you have to get insurance companies to pay for it, and then you have to get people to actually use it and adopt it in regular practice. So every technology follows these stages, and we're no different in that sense. One of the advantages that we have is that because there's this invasive measurement, and all we're doing is replacing that with a non-invasive version of the same test, then people have a reference and they understand what the test is, and they know how to interpret it. And they know what the results mean. So we're not going to them and saying, here's this completely new test. The machine has learned how to diagnose your patient for you or anything like that. We're saying, okay, well, this is the same test that you're familiar with, but now it's done non-invasively through a CT scan, through this computational method. They don't necessarily understand that at first, but through some education, they can understand how it works, and that gives them the confidence with the clinical trials that it's accurate and can be used clinically.
I want to begin to, as we draw to a close of this conversation, just go back to the software process and how cool this is, because you take, so just for people who have not followed closely, you take a CT scan, which is kind of like a video or a series of X-ray images. You take that collection of images and you put it through HeartFlow software. HeartFlow does three things. It creates a model of the arteries, and then it creates a physiology model around those arteries, and then it runs blood flow simulations around or within that physiology model. Did I miss anything in the explanation of how that works that you think would be interesting to the listeners?
Well, I think this is a very good summary. The additional thing that we do at the end is we automatically generate a PDF report. And this is really what the doctors are looking at. We're providing them with a bunch of set images and views, and we identify on these models where some of the issues with the blood flow could be. And this is very much the last stage, the entire reporting pipeline that we have and automation around generating these reports and giving them to the customers.
And it's not just the PDF report. We also provide an interactive 3D model that runs in WebGL in browsers that support that. So that enables a physician to not only look at a static report and have something they can put in the patient record, but also to interact with the results and query the blood flow calculation, query the model at whatever location makes sense for them to better understand the patient's disease and how they might go about treating them.
So you can also provide information about, like, based on that generated data, you can also provide suggestions for the treatment. Like, you don't just like say, here's the output and leave it to the doctor to infer a treatment. You can also say, maybe based on this model of the heart and the fluid dynamic simulations we ran, and based on patients who have been similar to this patient, stent might work, medication might work, other treatment might work. Can you make those kinds of suggestions at this point?
We never tell the doctors how to treat the patients, but because we're doing a non-invasive version of an invasive test, and that invasive test has been studied through multiple large clinical trials, people understand how to interpret the results. However, one of the things that we've shown and that we are working on currently is an application in which the doctor can interact with the model to change it to simulate different treatments. So, for example, if you have two blockages in series, one after the other, and the doctor says, okay, well, this is a severe problem, I need to put a stent in, they have to wonder, do I put in one stent? Do I put in two stents? If I put in one, do I put it on the first one or do I put it in the second one? And so what we're going to be able to provide them is an application where they can interact with the 3D model, and they can basically look at what happens if they open up the first blockage, and then we can recalculate the blood flow, and then they can say, okay, well, if I put a stent in there, that may be more effective than putting a stent in the second blockage, for example. And that's an application that will then allow them to look at these different scenarios, these different treatment scenarios virtually, and say, what would happen if I treat the patient like this? And that way they can, again, do everything through software, everything through computation, but figure out really what the best treatment is for the patient, instead of today where they have to use their judgment, but they don't always get it right in terms of figuring out exactly what the right stent location is or where to place it.
What I love about HeartFlow and this product that you're building is it's really an example of personalized medicine and where we are going and how these technologies that have seemed like really maybe incremental improvements, like or things that lead to incremental improvements, cloud computing, open source software, improved computer vision techniques, gradual increases in hardware capability. These things compound, and then they lead to things that look like just massive step changes. Like you look at HeartFlow, what HeartFlow does relative to the idea of an invasive procedure where you're taking the blood pressure before and after a coronary blockage. It's just really, I don't know. It's inspirational. I don't want to like pitch your product more than you guys are, but it's cool. So what are the other areas in the medical space that seem like they're poised for step changes? I don't know. What are the other things that are exciting in this space to you right now?
Well, first of all, thank you, Jeff. We're really excited about what we're doing too, and we really feel like you're right that all of these different technologies have reached a level of maturity that if you put them together, you suddenly get capabilities from the software, from medicine that were just not available before. And HeartFlow is really the first company to use fluid dynamics, patient-specific personalized simulations to help doctors make medical decisions and actually really treat patients. And today we've helped doctors, we've been used clinically in about 7,000 patients, in not only in the US, but in Europe and in Japan as well. So we're really doing something new. The FDA didn't know how to deal with us in the beginning. And so it's been a really great relationship working together with them to help them understand the technology and to understand and help design the clinical studies that have enabled it to work. To your question about other medical technologies, looking at it from a software perspective, like we do, I think that there are a lot of companies that are starting to apply machine learning in multiple different areas. If you look at IBM with Watson, they've really invested very heavily in healthcare. There are a lot of other companies that are using deep learning to help with diagnosis, help with quantification, but nobody that's yet taken the step of doing personalization the way that we are with physiological and computational modeling. 3D printing is another technology, though, that's really become very prominent in radiology in recent years, but still hasn't found the killer app that some other technologies have.
And I have to add, from a pure software engineering perspective, like it is very typical to be in that space and have software being deployed within hospitals. But because we're a cloud company, pretty much software as a service company, we get to use all these nice and cool technologies on a daily basis to solve a problem that is quite different from a lot of different software engineering companies. And it is mind thrilling to put at use all these technologies to something that is actually helping the patient in the long run. It is really making a big difference for all of us here.
Razik, Leo, thank you guys for coming on the show. It's been a pleasure talking to you.
Jeff, thanks so much. It's been a pleasure.
Thank you for having us, Jeff.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks again, Symphono.
Wow.